All right. Hey, there he is. All right, everybody, how we doing?
What's going on, Dr. Whitaker?
Not much.
Yeah, just chilling.
Just chilling. Yeah.
Yep,
Yeah.
getting ready for spring break and nonstop studying. You love it.
Oh, the best kind of break ever, right?
Yeah.
You'll look back and you'll miss it. Just not now.
Oh, I hope not. I miss it, Dr. Whitaker. At that time, I've gone insane. I'd much rather be going on a vacation. My sister's actually going to Turkey, and I was supposed to go with her, but
Yeah,
I couldn't.
there'll be time for Turkey in the future, right?
Yeah, I'm going to Lebanon in the summer, hopefully, if God is willing. So,
Yeah.
I like
Yeah,
the robe you got on.
Oh, you like it? Yeah, my mom gave me this for my 50th birthday.
It's actually nice.
Yeah, I like it.
Gives you the Godfather swag.
Yeah. Then
Yeah,
I got to change into my uniform. You're gonna like this too, I'm pretty sure.
I'll see.
Change into my uniform here. There you go. Yeah.
Teacher. Oh, okay.
Yeah.
I see it.
All right.
All right.
Should we keep that little intro in our video and
I don't mind.
get started?
I don't mind.
All
Yeah.
right. All right, everybody. We're gonna do the mechanisms from fall 21, and let's share the screen. Don't have the right one open right now. Oh, I do. Here it is. And we're starting off here. And this is one of those ones I warned you about, that there's a giveaway right here and here. That thing with the 1 is a strong base, and the strong base matches the leaving group here. I never mentioned why that's necessary. I just mentioned that it was a good visual for you to trigger your memory that this is a Claisen condensation. And it's a simple Claisen because there's only one reactant. And I never mentioned why it's important to have the base match the leaving group. It's because there's another reaction that's competing with the Claisen, and it's actually faster. It's with the OCH3 negative attacks the carbonyl. The electrons come up, they come back, and they kick off an OCH3 minus. Oh, but we chose the same attacker as the leaving group, so we don't even care that that reaction's happening, right? Cool. There you go. Now you know. But anyway, don't do that reaction. It doesn't get you where you need to go. We need the reaction that takes an alpha H. Chapter 19 is all about that. And we got a minus charge on our OCH3 minus that's attracted to the carbonyl. First step, you hit the carbonyl, the electrons come up to the oxygen. Red first. Oh, that's not working very well. Move everything down a little bit. Okay, red first. There we go. And blue second. Back to baby blue. And yeah, the electrons that you just put up on top of the O are gonna come and bounce back. Oh, they didn't start on a lone pair. There we go. And wait, I just did what I said I was not gonna do. Ha! That's too funny. Yeah, I just did the one where you put an OCH3 on and take an OCH3 off. The power of suggestion is strong. Let's get rid of those arrows. That's not what we're gonna do. As fun as it was. There we go. And yeah, we're gonna take the alpha H to get us to the Claisen. So red first, and we can't combine steps just yet. Lone pair on the alpha position, generating an anion. That's a carbon nucleophile. Okay, carbon nucleophile, and it's got ethyl and then CO2, CH3. There we go, and an anion right there. And it's going to attack what? There's nothing to attack. Oh, yes, there is. There's only one of these molecules for every 10 million of these. pKa says so. Look at lecture notes for that. I'm not going to go over it again. We got the unreacted version of the same molecule here. Looking ahead, putting a lone pair on there. First step, we attack. Pi breaks and becomes a lone pair. Second step, lone pair comes back. Leaving group leaves. And it's a catalyst leaving group, isn't it? The same leaving group that we started with in step 1. And you've generated a new bond. Very good synthesis going on. New bond right here. Boink. And we've got carbonyl, propyl, and it looks like this. In fact, it is that, but you can't pretend you're finished when you have a molecule that has a pKa of 10. Why is it 10? Because there's a carbonyl here that's alpha to that position and another carbonyl here that's alpha to the same position. And just make sure you know that's a carbon right there. And so acid base says you can't stop. Acid base must be obeyed. And you're going to generate the intermediate, which is the conjugate base of that product. There you go. Yeah. That was just dry. Looking for shortcuts. I don't need them always. O2C. Goes up to a C with a ethyl on it. It's got a minus on it. Got the other group here, the propanoyl group. And we need to put an H on there. Finally, HCl. We only use HCl one time, and it's right here. Grab the H, Cl minus leaves, and home free. Making the Claisen condensation product pictured here. Okay. Now you're thinking, oh, is he doing another Claisen here? He's got this thing matching the leaving group. But this is a different story now. I mean, the first thing that's going to happen here is for sure the acid base that we just undid here, we're going to redo here because pKa says it's not 25 anymore, it's 10. And we're just making an anion that can do several things. One, the most important thing on this test by far, I'm just going to give away a lot of secrets here. I'm always looking for excuses to do 1,4 addition on this test. You're going to do it 4 or 5 times. I'm not joking. So I'm making a nucleophile that will undergo 1,4 addition. And seeing as we got a lot of groups that aren't changing in this next part, let's do a quick little circle here. Maybe I shouldn't use baby blue. R. And CO2, CH3 is not that bad. Ethyl's not that bad. Let's go. And let's just make it all green. Right now we have CC, CO2, CH3, up to R. And remember that first carbon in R is a carbonyl, which means this is a very stable anion. We knew that. This has a pKa of 10, which means the anion's pretty stable. Not hard to make. Okay, it's a 1,4 nucleophile and it's also a good leaving group. And that's what it is. 1,4 nucleophiles, when given a choice, go to the beta carbon instead of the carbonyl carbon. Resonance. This is the 1,4 addition right here. 1,4 addition, 1,4 quotes. You don't need to write that on your test. Your mechanism showed it. And the green part's going to stay the same. I just always wonder if you can get away with this. Oh, that was nice. editing here. Lone pair's gone. Means the anion's gone. We gotta look at what we made a new bond to. Beta position here, new bond. Beta position has an ethyl on it. Beta position also goes to a C that has an ethyl on it. And there's now a double bond to a C. And that goes to an O minus. Make sure I didn't lose any carbons here. This whole thing has 1, 2, 3, 4, 5, 6, 7 blue. 1, 2, 3, 4, 5, 6, 7. We're happy. That's an enolate. And it happens to be the conjugate base of this guy right up here. There's an aldehyde down here. This is the enolate of an aldehyde, acid base. And you don't have to add HCl for this acid base because your nucleophile right here is not strong enough to deprotonate ethanol, but your enolate is. You don't have to separate the steps. It's a beautiful thing. And there you go. And there you go. Acid base puts H on the alpha position. You want to see the H? There it is. Came from there. Maybe we should make it purple. There. And now a whole bunch of fun's gonna go on. Oh, we got a rap song going now. Yeah, we got the old saponification, acidification, decarboxylation. This is the combination that gives that for the nation. All that good stuff. So saponification, we're gonna circle everything except for the ester. Saponification is for esters. R prime. Nucleophile hydroxide. Sure, that's a lone pair there. Electrons hit the carbonyl. Lone pair generated and an O minus. O minus resonates back. Kicks off the leaving group. Leaving group once again is a pretty strong base. So we've got R prime. R prime attached to carbonyl that has an OH on it. Draw that H off of the O, please, because you just generated a base at the same time. CH3O minus. And it's going to come and do what CH3O minus is going to do. Acid base. Saponification is now over. You've generated a carboxylate. Yeah, it's not using red arrow, confusing. Carboxylate, which I think we can avoid drawing R this last time. Carbonyl O minus. But after this, we're going to have to draw the whole deal so we can show the beta decarboxylation. That thing needs to become a carboxylic acid that is beta to a carbonyl. How do we do such a thing? Well, HCl will give us the carboxylic acid, and the beta to carbonyl takes care of itself in the R group. Let's draw out this molecule. What we have right now is what looks like this. Still think I can save a little bit of time if I do a circle within the circle. I know. All these circles get me dizzy. So pink we'll call RX. All right, so we got RX attached to a carbon that's got an ethyl, attached to a carbon that has a carbonyl and an O bonded to H. Make sure you show those bonds. And also connected there is a carbonyl with a propyl. And I think we got everything. Make sure you know that's a carbon there. All right, let's set up for a decarboxylation. Rx is way out of position here, but oh, don't be that way. That's fine. I don't like it. Rx needs to be closer. There. Beta decarboxylation happens because these electrons flowing in this circular arrangement of 6 pi electrons is a, I hate to say magical in science, but it is a magical thing. There's a lot of things favoring this kind of transition state. And the main thing is the electrons are in what do they call it? In synchronicity as they reach around with each other. But I'm just waving my arms. You don't need to talk about that. You generate an enol, and you've got an O bonded to an H here with a double bond now here. Your CO2 happened during this step. This carbonyl now, this one right here is part of CO2. No bond there, no bond to H, just C with 2 O's. And we've got Rx off of here. And we got ethyl. And that pretty much looks like this. Here's your Rx. There's your ethyl. Enol needs to become ketone. And you're not going to make me wait 5 seconds for it to say tautomerization, right? So yeah, it's time for tautomerization. How do you know it's an acid catalyzed tautomerization? Well, we're still at the stage where HCl is present. So this is the acid catalyzed tautomerization. HCl provides a proton to the alpha position. Cl minus grabs the H from the enol. That's a lazy arrow. That's not. There we go. Start at that lone pair. Sigma becomes pi. Old pi breaks and picks up a proton at the alpha position. There you go. Nice. That's this alpha position. This alpha position will now have a H instead of the carboxylate ester. And that is true story. Yeah, there's the H is going here. I think that's everything. Yeah. Good one. Lots of points. 22 points right there. And we're going to come back and do 6E, I believe. And yeah, we're ready for 6E, where we're going to do a Robinson annulation. We're going to do, this is an enamine. Enamine's going to do a 1,4 addition. I don't think we've seen one of those before. But it definitely added to the beta position here and not the carbonyl. So 1,4 addition again. And then hydrolysis. We better be good at hydrolysis of iminium ions. So we're going to stop our share and come back and do this. Adios.